So to summarize EEG and ERP, these electrophysiological techniques that have a lot of clinical applications, they're very good for clinical applications because they do give you significant information about state, about whether you're awake, asleep, what sleep stage you may be in, whether you're in a coma. They also give you information about seizure activity in terms of, to some extent sort of localizing focal seizures, one hemisphere or another, or maybe even one, lobe or another. They are cheap techniques typically because they don't involve, big machines, really. There is the expense, obviously, of people who are trained and skilled at reading the information in the EEG, although there have been a lot of advances in terms of software, in terms to be able to identify regions of interest in an EEG recording where the skilled clinician can actually focus in and give more of an assessment as to whether there's seizure activity or what an issue might be with that recording. It's also a relatively non-invasive technique. I mean, they got to scratch your scalp, right? But it's not like they have to open your brain, get into your brain. It's also a really good technique for giving you timing information about neuronal activity. Because on those graphs I've been showing, right, those tracings I've been showing, the x-axis in terms of the time, in terms of these changes in electrical activity over time, is in milliseconds. I mean, it's really giving you sort of millisecond to millisecond changes in brain activity, which means it has terrific what we call temporal or time resolution. So it's got excellent temporal resolution. What you might notice, however, is that it doesn't have very good spatial resolution. So EEG can be construed or can be considered an imaging technique in the sense that it's actually giving you a functional interpretation, of what's going on. It's telling you whether somebody's having a seizure or whether they're alert or relaxed, right, or asleep or awake. However, the pictures, right, the images aren't all that good, right? It's got great time resolution, millisecond to millisecond, but the spatial resolution is not very good. And part of that problem is because of something called the inverse problem. So if you are recording a certain, set of data, like electrical data from the surface of the scalp, right? It turns out that you could posit multiple sources, generator sources, like activity sources within the brain, actually, that would generate the same pattern. So it's not a direct, to go back and determine precisely, which regions of the brain are giving rise to the particular tracings that you're seeing on the scalp is a difficult problem. It's called the inverse problem. With things like the auditory ERP, a lot of animal research has helped us to specifically localize this peak to activity in this structure. So we know because we've used other, in this case, electrophysiological techniques, recording techniques, to confirm that what we're detecting on the surface means activity in that structure. But in general, you can't always tell that, from the recording that you get from the whole brain. And again, the other thing to keep in mind, it's not a recording from the whole brain, right? It is actual electrical activity of neurons, which is terrific. It has terrific, temporal resolution, but not very good spatial resolution, and it's a limited recording. It's only mostly, cortically generated, and it's mostly the gyri, and it's mostly, neurons that are oriented in a particular direction.